All right, in this video, I'm going to cover section 5.2 conditional probability distribution with two random variables. So 5.2 conditional probability distribution. Okay, so second. Yeah, so when two random variables are defined in a random experiment, so knowledge of one can change the probability that we associate with the values of the other, right? So think about this. So in the chapter 4, we learned the conditional probability with one random variable, right? Okay, and then if we just extend that concept to the conditional probability with two random variable, B, B, or A, okay. Then this is going to be, for this is the conditional probability for event A and B. A and B are events, okay. So we learned this one in chapter 4. So now the probability that B or A, whatever, B intersect with A over probability of A, isn't it? Okay. So this definition can be applied with the event A defined to be random variable, random variable X equals lowercase x, and the event B defined to be the another random variable Y equals capital letter Y equals lowercase y. What I mean is we can apply this one to the conditional probability with the two random variables by considering A as the, probability that, probability that, like this, considering A as the x equals random variable x is a lowercase x, and this one as y is equal to lowercase y. So x equals x bar, y equals lowercase y is equal to probability that x equals lowercase x, and then y is equal to lowercase y over, okay. Can you see that? Wait a second. Yeah. And then probability that x is a lowercase x. Okay. So keep in mind this. So now, let's see. Yeah. Okay. So let's see example 5.5. So let's see. Example 5.5, conditional probability for mobile response time. We saw this example in 5.1. We're going to use the same table shown in the example 5.1. Okay. So then let's see. Oh, can you see that? Oh. So example 5.1, 5.5, example 5.5. The problem asks you to find out probability that y is equal to 1 or x equals 3. Okay, so that is equal to, so example 5.1 was this. Example 5.1, give me a second. So the y represent the response time, and the x represent the number of bars of signal strength. Okay, so please read the example 5.1 in textbook. Okay, so we want to figure out the probability that the number of bar in signal strength is 3, and then the response time is 1 millisecond. And that's going to be probability that x equals 3, and the y equals 1 over probability that x equals 3, right? So this is going to be what? This is, we can figure out this on by applying the joint probability distribution, right? 3, 1 over fx and 3. Okay. So now, then just by looking at the table in 5.1, we can see that that joint probability when x is 3 and y equals 1 going to be, excuse me, going to be 0.25, and the denominator going to be, this is what? This is a marginal probability distribution, okay? So what that means, this one, that is equal to what? F, oh, sorry, sigma, okay, y, and then f x y, okay, and then 3 comma y, okay? So it means that, by the way, the response time, possible value of the random variable y response time is 1 through 4. So that is equal to fxy and then 3 comma 1 plus fxy and then 3 comma 2 plus fxy and then 3 comma 3 plus f xy and then 3 comma 4. Okay, so adding them out, we'll get the what? Let me see. Let me see. Let me take a look at the table. So we got the 0.55. Okay, so that is equal to 0.454. Okay. So similarly, you can find out the answer for other question in exam 5.5. So the example, second one is this first question, and the second question, probability that y is equal to bar x equals 3. This is a probability that y equals 2 given that x equals 3, right? This is equal to probability that x equals 3, comma y equals 2 over probability that x equals 3, right? So that is equal to fxy and then 3, comma 2 over fx3. Okay, so that is equal to, this is marginal probability of x. This is join the probability distribution, right? Or you can join the PMF at x is 3 and y equals 2. So I believe we can find out this one and this, right? By looking at the table in the example 5.1. So the answer is going to be 0.2 over 0.55, so which is 0.364. Okay. So now then, let me see. All right, so the generalize this. So we can define the conditional probability mass or density functions. So given discrete or continuous, okay, random variable x and y with joint PDF or PMF, okay, joint PDF or joint PMF, okay, and the okay fxy x comma y, okay, the conditional probability PMF or PMF, okay, or PDF, let me just PMF PDF of y given x is lowercase x is what? fxy, oh, sorry, fy bar x, lowercase x. This is a capital letter y, this is lowercase x. Y is equal to fxy and then x comma y over marginal probability of x, probability distribution of x. Okay, definitely fx of x must be greater than 0. Okay, so let's see property of the conditional PDF. So property, okay, the PDF going to be what, first one? Yeah, so yeah, conditional probability is the PDF, right? So fy bar x of y, that must be greater than or equal to 0. Okay, and then the second one is what? The sum of all of the conditional probability must be equal to 1, which means the integral of conditional probability must be equal to 1. Okay, the last one, probability that y belong to the subset, okay, in the range of y. This is subset, okay, a subset in the range, okay, of y, okay, where x is a lowercase x. That is equal to integral b and then f y bar x and then y and then dy. Okay, so let's see example example 5.6. So let me share. So example 5.6. Yeah, example 5.6. So look at this conditional probability. All right, so for the random variables that denote times in the example 5.2, remember that the example 5.2, the time the machine will connect the server, right? And then the other variable, random variable, denote the time that the machine recognize you as a user, right? So determine the conditional probability density function for y given that x is lowercase x. Okay. So first, to figure out, right? So let's see, back to the here. All right. So if I using 5.6. All right. So first one, fxy was x comma y. The joint PDF was given is like this: 6 times 10 to the negative 6 times e to the negative 0.001x minus 0.002y, and then d, not dx. Yeah, this is a joint PDF, right? And then we want to find out the what? Question is to find what fy, I mean conditional probability of y given that x, right? Y. This is gonna be what? By using definition of the conditional probability with the two random variable, gonna be what? Joint PDF over and the marginal probability of x, right? So the numerator is given, right? This. And then what about the marginal probability? That's what we have to find out. So this is gonna be so to find out. So we're gonna find out this one first. Okay. So fx of x, that is equal to, what's the definition of marginal probability of x? The integral, right? And then let's say to what? Integral of what? Integral of join the PDF with respect to y, because this is a marginal probability of y, right? So for fixed value of random variable x, we're gonna evaluate integral with respect to y. That's the definition of marginal the PDF of x. Okay. So, but in this, then to figure out the lower limits and upper limit, and let me write down the join the PDF first. 6 times 10 to the negative 6 e to the minus 0.001x minus 0.002y and then dy, right? So to figure out the lower limits, upper limits, we need to figure out what the domain of that joint PDF, right? So we already know the domain of that joint PDF, which is here, right? This is this is random variable x. Vertical line represent the random variable y. Okay, this is x, y equals x. Okay, so now then, what's the lower limits, upper limits the along the x axis, y axis, I'm sorry, from the x to infinity, right? Here's x, infinity, right? So now this is going to be what, x to infinity. Okay, that makes sense, right? Because this is improper integral, and then when you evaluate this, we're going to get the function of x. You see that? This is a marginal PDF, but in calculus, we can say that this is what, a function of x. So we should get the function of x, I mean, algebraic expression of x somehow on the right-hand side. Okay. So now then we evaluate the improper integral. Okay. Then we're gonna find out entire of this, but let me simplify this one. Okay. So first one, let me bring out 10 to the negative 6, and then divide the exponential term as e to the negative 0.001x times e to the negative 0.002y. We did many times in previous section. Okay. So, and then we take out the e to the negative 0.001x out of the integral. Okay. So we got x2 infinity e to the minus 0.00200, okay, 2y and then dy. Okay. Now this is equal to 6 times 10 to the negative 6 and the e to the minus 0.001x. And then what's the integral of this? That's going to be e to the minus 0.002y over minus 0.002 and then x2 infinity. Since this exponential is decreasing function, so as y approaches infinity, this fraction approaches 0. So we're gonna get this, gonna be what? This is gonna be e to the minus 0.002 x over 0.002. Okay. All right. So now what we get is this. This is equal to, yeah, we don't have enough space. Yes. So that is equal to what? 6 times 10 to the negative 6 times 0.002, which is 0.003. Okay. 0.003 times e to the negative 0.001. Give me a second. So what happened? So the 0.003 times e to the negative 0.001x times e to the negative 0.002x, right? So then we're going to get e to the minus 0.003x, right? So yeah, definitely x is greater than 0 because x represents time, right? So now we're going to plug in this one into the definition of conditional probability. Okay, so then we get the what? 0.003, so 0.003 e to the minus 0.003x, and top one going to be 6 times 10 to the negative 6 e to the, okay, minus 0.001x minus 0.002y. Simplifying this fraction, then we're going to get this. This finally, the answer is what? I mean, f y bar x of y, that is equal to 0.002, because 6 times 10 to the negative 6, 6 times 10 to the negative 6, and then over 0.003, simplifying the fraction, we're going to get 0.002. and then times e to the point 002 2x minus 0.002y. Okay, so here definitely x is greater than 0, and then definitely y is what? Y is greater than x. Okay, so now second so now using that one, let's find once we figure out conditional probability, right? So let's see. Yx. Okay. Yeah, let's see. The second question in example 5.6. Okay, so give me a second. All right, so determine the probability that y exceeds 2000. Okay, given that x equals 1500. So that is determine probability that y is greater than 2000 given that x is 1500. So yeah, conditional probability density function is integrated as follows. So we'll see. Okay, so as you can, yeah, let me explain this one in my sketch paper. Okay, let's see, stop here. All right, so right there. Okay, the second question is to determine probability that y is greater than 2000 given that x is 1500. Okay, so that is equal to, yeah, so this is equal to what? Integral. I mean, so look at this. This is a conditional probability, but not like the probability that y equals a number, but y is greater than 2000. That's why we have to take integral. Okay, so y is greater than 2000, so 2000 to infinity, right? This is integral with respect to y, dy here, and then we do the integral must be conditional probability of y, f y bar x, okay, and then of y, and then dy, but see, x, random variable x is fixed as what? 1500. So that is 1500. Okay. So now that is equal to, we already got the conditional, we already figured out conditional probability, right? Right there. Which one? Oh yeah, here. Right, see? So we're gonna plug in this one here, and then I'm gonna substitute 1500 into x. So then this is equal to integral in 2000 to infinity, and the 0.002, and the e to the 0.002 times 1500, okay, minus 0.002y, and then dy, isn't it? Okay, so now this is equal to, so we're gonna take out, okay, I mean bring out that constant term, so we got 0.002 e to the, oh, this one, so 0.002 times 1500, that's gonna be what? 3, right? 0.002 times 1500 is 3, so e cube. So integral 2000 and infinity, and then e to the minus 0.002y and dy. Okay, so that is equal to what? This is equal to 0.002 e cube, and then minus 0.002 e to the minus 0.002y, and then 2000 and then infinity. Okay, so now yeah, so as y approaches infinity, this exponential approaches 0, so that fraction gone, so that is equal to 0.002 e cubed times what? 0.002. Okay, so and then e to the minus 0.002 times 2000. Okay, so that's going to be e 0.002, 0.0 cancel them out, right? So what is this? This is e to the negative 4, right? Okay, so we got this e to the negative 1. Okay, so give me a second. Yeah, okay, e to the negative. I mean, approximately this is the give me a second. So this is approximately 0.367A, but let me say just 0.368. Okay. Right. Now, let's figure out the conditional mean and variance. So let's see my lecture note. So conditional mean, okay, and variance. So the conditional mean, okay, conditional mean of y is given that x is lowercase x. Okay, this is denoted as what? As expected value of y bar x, or you can say, or mu y bar x. Okay, that is mu y bar x. This is equal to e over y, right? And then y times f y bar x, and then y, and then ty. Okay, so that means the integral, I mean, lower limits, upper limits are the range of y. Okay, so that's all that depends on problem. So, and then conditional variance. So, I mean, detail the expression of the conditional variance should be in the lecture note. Please look at that. The what v, by the way, v y bar x. That means conditional variance of y given the x uppercase x equals lowercase x. Or you can say the sigma square, the y bar x. Okay, that is equal to integral y, and then guess what? Y minus mu y bar x. That's the conditional mean, right? Square times f y bar x, and then y, and then ty. So that is equal to integral y. And then expand this, and then simply separate the two multi integral terms, and then cancel them out. And then we got y squared f y bar x of y minus dy. Okay, sorry. Let me see, dy minus mu y bar x squared times integral y, and then f y bar x, and then y, and then dy. Okay, so you see that here? What? This is gonna be what? By the property of the conditional probability, this equals 1, right? Okay, this is 1. I mean, okay, so this is the simplified form, I mean, short expression of the conditional variance. Let's see example 5.7. See, yep. So example 5.7. Okay, for the random variable that denote times in example 5.2, yeah, so remember that example 5.2, the two random variable y and x. So the what is this? X represent the what? The time the machine they connect the server, and then the another random variable y denote the time the machine gonna recognize the user you as a user. So the conditional okay, determine the conditional mean for y given the x is 1,500. And then, okay, and then conditional probability density function for y was determined in example 5.6. Yeah, I'm going to use that. And then the, see, because fy, see here, because fy bar 1500 of y is non-zero for y is greater than 1500. So we can say they're gonna calculate this. So let's see. So what does that mean? Because y, I mean conditional probability, y given that x is 1500 is non-zero for y is greater than zero. Y is greater than 1500. What does that mean? Let me explain this. So, all right. So here, so expected value. So expected value of y bar x equals 1500. Okay, so that is equal to, I mean, so we're gonna find out this, right? That's the quotient in the problem, example 5.7. All right, so now this is equal to then what? By definition of the what? The conditional mean, which is this, right? So we have to take integral y times fy bar x, y, and the dy, isn't it? Okay, but x is given, which is 1500, right? Okay, that's 1500. And then also we need to figure out the what limits of integration, lower limit, upper limits, right? So then look at this. Let me draw the domain of joint PDF. So yeah, x, y, right here. This is y equals x. So that's the domain right here. Okay. But x is fixed as 1500. So let's say here's 1500. Okay. X is fixed. Okay. So then what? Then we want to take integral with respect y. Then range limits of integral with respect y going to be what? Starting from 1500 to what? Infinity. Okay. So see. Okay. So now then, give me a second. Yeah. So it looks like this is a kind of line integral. If you study in calculus 3. Okay. So now this is going to be 100, 500. Okay. So and then this is infinity. All right. Let me see. Give me a second, and then, yep. All right. So, second. We're so okay. So, but you may say that, all right. So this is the conditional probability. But how the limits of integration of conditional probability determined by just the determined by the domain of joint PDF. Well, if you can say that, then you look at this. Conditional probability is defined as like this, right? And the x is greater than 0 and the y is greater than x. Look at the y is greater than x. So if x is 1500, the y must be greater than 1500. That's why we need to evaluate the integral from 1500 to infinity. So now, okay, so let me see. So yeah, this is equal to what then? 1500 to infinity y times fy bar x. I mean, conditional probability was what? This is 0.002, right? Times 0.002 e to d 0.002 times 1500, right? Minus 0.002 y. And then dy. Okay, dy. Now, so the first one, I'm gonna, yeah, so first one, we're gonna do what? What are you gonna do? See that? 0.002, and then that exponential is constant, right? So I'm gonna take them out. So that is equal to 0.002 times, then this is gonna be EQ, right? Okay, and then in a graph, 1500 to infinity, and then y times e to the minus 0.002y and the dy. Okay, so now you see that how can you evaluate the integral? See, look at the integral. This is a polynomial and the exponential function. So the integral is consists of the product of two different type of functions that we gotta use integral by part. So I'm gonna use the integral by part. So let's say remember the integration by part. This is u and dv is equal to uv minus integral v du, right? So here let's say u is equal to what y. Yep. Then du is just dy. Okay, and then du, let's say dv as e to the minus 0.002y. Okay, and then dy, then v is equal to integral of entire of this is what? E to the minus 0.002y over minus 0.002. Okay, so then u times v is what? Y times here, y times e to the minus 0.002y over minus 0.002, and then 1500 to infinity. Oh, excuse me. Then minus integral v du. So v is e to the minus 0.002y over minus 0.002 times du is just dy, right? And then 1500 and then infinity. Okay, so excuse me. Now, yeah, we let me just keep going. Okay, right here, and this is equal to. All right. So, now let me see. Okay, so now then, what we look at this. As y approaches infinity, this fraction approach 0, but this one approach infinity. So we got one of the indeterminate form. I know you may don't remember what it is, but we learned in calculus 1. Okay, so this is one of the indeterminate forms, then we have to change the form, right? So let me see, there's gonna be, I need a second. So now then, this is gonna be this. We can say the limit of what? Y, I mean 1 over minus 0.002. Sorry, this. Let me write down again. I'm sorry. So this is 1 over minus 0.002 times the limit of y over e to the 0.002y, and then as y approach infinity. Okay, and then minus 1500, because I just plug in 1500 into dy. So we get the e to the minus 0.002 times 1500 over minus 0.002. Okay, all right, that's just first term, and then minus, okay, the minus integral 1500, the infinity, and the e to the minus 0.002y over minus 0.002, the dy. Okay, so what is this? So as y approaches infinity, numerator approaches infinity, and then denominator also approaches infinity, right? Okay, so I just just rewrite this one entire derivative is like this. So that infinity times 0, that in the indeterminate form has been, you know, to change the limit of infinity over infinity. I mean, infinity over infinity form. Okay. So then what? We can use L'Hopital rule. So applying the L'Hopital rule, so that is equal to, remember that? L'Hopital rule is the limit of, yeah, just, yeah, find the L'Hopital rule in calculus 1 book, okay? So this is a minus 1 over 0.002. And then L'Hopital rule says that if the limit of the rational function in numerator denominator both approach infinity, then that limit is equal to the limit of derivative of numerator over derivative denominator. So it's going to be 1 over derivative of numerator going to be what? 0.002 times e to the 0.002y, okay, as y approaches infinity. Okay, so y approaches infinity, then that exponential approaches infinity. So we got 1 over exponential term approaching infinity. That's going to be 0. So this is 0. So now, that term just gone, and then simplifying this, we're gonna get what? Plus, right? And then 3 times, you see? Let's see. Yeah, so let me say let me simplify later. Okay, 0.002, and the e to d, that's gonna be e cubed minus 3. Sorry, cube. Okay, and then minus. Excuse me. The minus, and then c, and the derivative is gonna be what? E to the minus 0.002y over minus 0.002 square, and then 1500, and then infinity. Okay, so now then, yeah, so that is equal to then what? Let's see, let me copy just this one over 0.002 e minus 3, and then minus, because y approaching infinity, then what? As y approaches infinity, then the fraction just goes 0, right? And then, so the second term gonna be left. What I mean is this: as y approaches infinity, this fraction is 0, approaches 0. So we the first, I mean that evaluation, the first term gone. So the second term, which is what, which we can get by substituting 1500 into y, gonna be left. So so minus e to d minus 0.002, and then 1500 over minus 0.002 square, and then that should be plus, right? Okay. So then that is equal to 1500 over 0.002, and the e to the negative 3, and then plus, and the e to the negative 3 over what, minus 0.002 square is nothing but just positive 0.002 square. Okay, so that is equal to e negative cube negative 3, and then 0.002, okay, times 2000, you can say it. Yeah, how did you get this? Yeah, so or just, yeah, you just, yeah, you can use calculator, okay, or just simply just well, this is equal to, or you can say just e to the negative 3 times 1500 over 0.002 plus 1 over 0.002 squared. Okay, you can then just simplify this one using calculator. It doesn't matter. Okay, either one. Okay, so give me a second. Oh, second. Yeah. Now let me see. Yeah, the next one, we gonna give me a second. Yeah, so the next time I'm gonna solve the exam 5.8 independence of random variable. Okay, now definitely I'm gonna explain about the independence. So because we deal with two random variable, right? So what if the knowledge of the value of random variable x does not change any of the probability associated with the another variable y? In that case, we say that the uh, the two random variables are independent. So then, how can you find what happened in that case? Two random variables are independent. What happened to the marginal probability of y, marginal probability of x? Again, we see example 5.8, independent random variables. Okay, so that's for today. Okay, so now, yeah, see you next time.